Welcome. You have nothing to do right now, nowhere to be, nothing to solve. Let your body settle into wherever you are resting. Let your breathing slow, your thoughts loosen, your shoulders drop. Tonight, we are going to travel very far together, not with urgency, but with the unhurried ease of something drifting gently outward through the dark. Simply listen and let the words carry you. The idea of sending a spacecraft beyond the solar system was first seriously proposed in the 1960s. In those early years of the space age, scientists and dreamers began to wonder whether a machine built by human hands could one day leave the sun's family entirely. It was a quiet, patient kind of ambition, not urgent, not rushed, but steady and deep. The thought settled into the minds of researchers like a seed finding soil, and it would take years to grow into something real. Engineer Gary Flandreau discovered the rare planetary alignment that made the Grand Tour possible in 1965. While working at the Jet Propulsion Laboratory as a young graduate student, Flandreau was mapping possible trajectories through the outer solar system. He noticed something extraordinary in his calculations. The outer planets were drifting into an alignment that would allow a single spacecraft to visit all of them in one long looping journey. It was a discovery made quietly, on paper, with pencil and patience. The planetary alignment Flandreau identified would not recur for another 176 years. The outer planets moved so slowly in their vast orbits that this particular gathering, this brief celestial convenience, was a rare gift of timing. If the opportunity were missed, no one then living would see it come around again. There was a long, unhurried window, but it had edges, and the people who understood this began, very gently, to plan. Early mission concepts were called the Planetary Grand Tour, and envisioned 4 spacecraft. The plan was generous in its ambition, 4 probes fanning out through the outer solar system, each one tracing a different path among the giant worlds. Scientists sketched trajectories that would carry these machines past Jupiter, Saturn, Uranus, Neptune, and perhaps even Pluto. It was a vision of thoroughness, of wanting to see everything at once, while the window of alignment held open like a door in the dark. Budget cuts in the early 1970s reduced the Grand Tour fleet from 4 probes to 2. The larger vision had to be trimmed, made leaner, made to fit within what was possible. 2 of the 4 planned spacecraft were set aside, and the mission was reshaped around a smaller, more focused pair of travelers. There was a kind of quiet resilience in this. The dream did not disappear. It simply condensed, becoming more concentrated, more essential. The 2 surviving spacecraft were officially named Voyager 1 and Voyager 2. The name Voyager carries within it something ancient and open. It speaks of journeys undertaken without a fixed return, of movement for the sake of discovery. These 2 machines, still being assembled, still earthbound, were given names that already pointed toward the infinite. There is something tender in that, naming a thing for where it is going before it has even left the ground. Both Voyagers were built by the Jet Propulsion Laboratory in Pasadena, California. Nestled in the foothills of the San Gabriel Mountains, this laboratory has long been a place where human ingenuity reaches outward into space. Teams of engineers and scientists worked for years in clean rooms and assembly bays, fitting together components that would one day travel farther than anything ever made. The mountains outside were still and green, while inside, something extraordinary was being born. Each Voyager spacecraft weighs approximately 825 kilograms at launch. That is roughly the weight of a large motorcycle or a grand piano, something a person could stand beside and reach out and touch. It is a modest weight for something meant to outlast civilizations. There is a humbling simplicity in that number, a reminder that the most enduring things are not always the heaviest. These were not massive machines. They were precise, considered, and built to last. The spacecraft body is built around a 10-sided aluminum framework called the bus. This central structure, a decagonal ring of lightweight metal, forms the spine of each Voyager, the quiet core from which everything else extends. Instruments, booms, antennas, and power systems all reach outward from this central frame, like branches from a trunk. It is an elegant kind of architecture, spare and functional, designed not for beauty, but achieving it anyway in its purposeful symmetry. Let your body settle a little more deeply now. Feel the weight of your limbs, the warmth beneath you, the slow rise and fall of your breath. There is nothing you need to hold on to tonight. Let each thought drift away as gently as a leaf carried on still water. You are safe, you are resting, and all is well. Simply let yourself be here, breathing slowly, drifting softly toward sleep. Each probe carries 3 radioisotope thermoelectric generators for power. These 3 cylindrical units extend from the spacecraft on a long boom, angled away from the sensitive instruments to keep their gentle heat from interfering with measurements. Together they form a quiet, self-contained source of energy. No solar panels needed, no sunlight required. Even in the deepest dark, where the sun is barely a bright star, these generators hum on, steady and unhurried, drawing power from the slow transformation of matter itself. The radioisotope thermoelectric generators use the radioactive decay of plutonium-238 to generate electricity. Deep inside each generator, a core of plutonium pellets releases heat as atoms slowly and naturally transform over time. That heat flows through thermoelectric converters, materials that turn a temperature difference directly into an electric current. No moving parts, no combustion, no flame. It is one of the quietest forms of energy generation ever devised, a slow, patient unraveling of matter, powering instruments billions of kilometers from home. At launch, each radioisotope thermoelectric generator produced roughly 157 watts of electrical power. 3 generators together gave each spacecraft around 470 watts to work with, enough to power a few household light bulbs. It is a modest amount of energy to carry across the solar system, and yet it has proven sufficient for decades of discovery. The engineers who designed these systems understood that efficiency and endurance matter far more than abundance when the journey ahead has no foreseeable end. Voyager carries a suite of 10 scientific instruments, including cameras, magnetometers, and spectrometers. Each instrument was chosen to answer a different question about the worlds the spacecraft would encounter, the chemistry of atmospheres, the shape of magnetic fields, the texture of charged particles drifting through space. Together they form a kind of sensory array, a way of reaching out and touching environments no human hand could ever approach. The spacecraft would become, in a very real sense, an extension of human curiosity given physical form. The imaging system uses Vidicon tube cameras rather than modern digital sensors. These cameras work much like a television camera of their era. Light strikes a photosensitive surface inside a vacuum tube, and the resulting electrical signal is read out line by line to form an image. The technology was already mature and well understood, chosen for its reliability over novelty. And yet, with these humble analog eyes, the Voyagers would return images of worlds that had never been seen up close, images that changed what humanity knew about its own solar system. A plasma wave subsystem listens for radio emissions in interplanetary space. This instrument carries long, slender antennas that extend outward from the spacecraft like delicate whiskers, sensitive to the faint electrical oscillations that ripple through clouds of charged particles. In the vast spaces between planets, plasma is never entirely silent. It hums and murmurs with wave patterns that carry information about the invisible environment surrounding the probe. Scientists on Earth listen to these recordings and hear in their own way the voice of interplanetary space. The cosmic ray subsystem detects high-energy particles arriving from outside the solar system. These particles, accelerated by distant supernovae and other powerful events far across the galaxy, stream inward from every direction. By counting and measuring them, scientists can learn about the energetic history of the cosmos beyond our sun's reach. The instrument is patient and tireless, registering each arriving particle like a quiet archivist, noting each new entry in a ledger that has been filling for nearly half a century. The light entering your eyes tonight once traveled through the same vast space these particles cross. The low-energy charged particle instrument measures electrons and ions near the spacecraft, where the cosmic ray subsystem looks at the most energetic arrivals from the galaxy. This instrument is attuned to the quieter, lower-energy population, the electrons and ions that drift and pool in the regions around the probe. Together, these two instruments paint a layered picture of the particle environment, from the faintest whisper to the sharpest signal. They work in complement, the way a listener might attend to both the melody and the undertone of a piece of music heard from a great distance. An ultraviolet spectrometer was included to study the atmospheric compositions of planets. This instrument breaks ultraviolet light into its component wavelengths, reading the chemical signatures hidden within, each element and molecule leaving its own distinct mark in the spectrum, like a fingerprint written in light. As Voyager swept past Jupiter, Saturn, Uranus, and Neptune, this spectrometer quietly read the chemistry of their skies, identifying hydrogen, helium, and more complex compounds drifting high above cloud layers no spacecraft had ever visited. It turned light itself into language. The photopolarimeter on Voyager 1 failed early in the mission. This instrument had been designed to measure the intensity and polarization of light reflected from planetary surfaces and atmospheres, offering a window into the texture and composition of worlds seen from afar. When it fell silent, scientists accepted the loss with the quiet patience that deep space work requires. The remaining instruments carried on, and the mission continued its long, unhurried journey outward, still rich with discovery. There is nothing you need to do right now. Nowhere to be, nothing to solve, nothing to carry forward into this moment. Let your shoulders settle a little heavier. Let your breath find its own slow rhythm, unhurried and easy. With each exhale, the day grows a little more distant, like a shoreline receding gently behind a vessel moving out to sea. You are safe here, still and warm, drifting softly toward rest. Each spacecraft carries an 8-track digital tape recorder for storing data. In the 1970s, this was the most reliable technology available for holding information gathered during planetary encounters, when data flowed in faster than it could be transmitted home. The recorder spooled magnetic tape back and forth, patiently holding images and measurements until ground controllers were ready to receive them. It is a reminder that extraordinary journeys are made possible by the most practical, unassuming tools. Voyager 2 launched first on August 20th, 1977, aboard a Titan III E-Centaur rocket. The rocket rose from Cape Canaveral in the warm Florida summer, carrying its precious cargo upward through blue sky and then into the blackness above. Ground crews who had spent years assembling and testing the spacecraft watched it diminish to a bright point of light, then disappear entirely. That moment marked the beginning of a journey that would outlast every expectation placed upon it. Voyager 1 launched 16 days later, on September 5, 1977. The two spacecraft were now both underway, separated by just over 2 weeks, but destined for very different paths across the solar system. In those early days of flight, they were still close to home by cosmic measure, crossing the inner solar system through familiar sunlit space. Yet already the long silence of the outer planets lay ahead of them, patient and waiting. Despite launching second, Voyager 1 was placed on a faster trajectory than Voyager 2. Mission planners had designed it this way deliberately, angling it onto a steeper, swifter arc that would allow it to reach Jupiter and Saturn ahead of its twin. The two spacecraft were not racing. They were simply assigned different roles in a carefully choreographed exploration. Voyager 1's speed would carry it further and faster into the dark, eventually making it the most distant object humanity has ever sent into space. The launch window for both probes was extremely narrow, lasting only a few weeks. The rare alignment of the outer planets that made the grand tour possible was not forgiving of delays. If either spacecraft had missed its window, the opportunity would not have returned for another 176 years. Engineers and mission planners worked with extraordinary care to ensure everything was ready in time. That precision, that quiet diligence, is part of what makes the Voyager story so enduring. During the long cruise to Jupiter, engineers uploaded new software to improve the performance of the cameras. This was an early and remarkable example of updating a spacecraft's capabilities while it was already in flight, traveling millions of kilometers from Earth. The new programming allowed the cameras to compensate for the spacecraft's motion during long exposures, resulting in sharper images than the original design would have produced. It was a quiet act of ingenuity, invisible to the world but vital to the mission. Voyager 1 crossed the asteroid belt without any damaging impacts. The region between Mars and Jupiter is populated with countless rocky fragments, yet the space between them is so vast that the chance of a collision was always very small. Scientists had calculated the risk carefully and found it manageable, but there was still something quietly reassuring about watching the spacecraft emerge unscathed from that ancient field of debris. It passed through like a thought, drifting through a dark and empty room, undisturbed, unhurried, whole. The onboard computers on each Voyager have a total memory of about 69 kilobytes. By today's measure, that is almost incomprehensibly small. A single photograph on a modern phone holds thousands of times more information. Yet with this modest store of memory, the spacecraft navigated the outer solar system, managed 10 scientific instruments, and returned discoveries that reshaped our understanding of the planets. It is a reminder that capability is not measured in size, and that extraordinary things can be carried in very small vessels. Voyager 1 made its closest approach to Jupiter on March 5, 1979. After nearly 18 months of quiet travel through the dark, the spacecraft arrived at last beside the largest world in our solar system. It swept within 278,000 kilometers of those swirling amber clouds, instruments humming softly, cameras drinking in the light. The encounter lasted only a matter of hours at its closest, yet in that brief passage, an entire new portrait of Jupiter began to emerge. Voyager 2 followed with its own Jupiter flyby on July 9, 1979, arriving just over 4 months after its companion. By then, scientists had already begun absorbing the wonders Voyager 1 had revealed, and the second spacecraft arrived ready to look even more closely. Its trajectory carried it along a slightly different path, offering fresh angles on the moons and the great swirling atmosphere below. Together, the two flybys wove a richer, more layered understanding of this enormous world than either could have achieved alone. Let yourself settle a little more deeply now. There is nowhere to be and nothing to hold on to. Feel the weight of your body resting, fully supported, sinking just a little further with each slow breath. Your thoughts may drift like distant signals, faint, unhurried, dissolving before they arrive. Let them go. You are warm, you are still, and the night is long and soft around you. Simply rest. The two probes collectively returned over 33,000 images of the Jovian system. 33,000 windows opened onto a world that had, until then, been little more than a bright disk in a telescope. Scientists received photographs of swirling storms, fractured moons, and ring arcs no human eye had ever seen. Each image arrived as a quiet gift, crossing hundreds of millions of kilometers of empty space to land in a receiver on Earth. The sheer abundance of new knowledge was, by any measure, staggering. Voyager discovered that Jupiter has a faint ring system previously unknown to science. Before these flybys, Saturn alone was known to wear rings, and astronomers had assumed it was unique in that regard. But the data returned by Voyager revealed a thin, delicate band of material encircling Jupiter, too dim to have been detected from Earth. It was a humbling reminder that even the most familiar objects in our skies still hold secrets, quietly waiting for the right eyes to find them. Jupiter's Great Red Spot was revealed to be a complex, turbulent storm system, unlike anything scientists had fully imagined. What had appeared from Earth as a smooth oval smear of color was up close a churning vortex of layered clouds and swirling eddies. Smaller storms spiraled around its edges, drawn into its vast circulation, and then cast away again. The storm had been observed from Earth for centuries, and yet it took a spacecraft passing by in a matter of hours to begin to reveal its true, restless nature. Voyager detected lightning in Jupiter's atmosphere for the very first time. The instruments recorded flashes deep within the cloud layers, illuminating the roiling gases from within like a lantern, held behind thick curtains. The lightning bolts were estimated to be far more powerful than anything seen on Earth, yet from the spacecraft's vantage point, they appeared only as brief, silent pulses of brightness buried in the amber murk below. There was something both familiar and deeply strange about finding such an earthly phenomenon in so alien a sky. The moon, Io, was found to have active volcanic eruptions, the first ever discovered on any world beyond Earth. Scientists had not expected to find such dramatic geological activity on a moon, and the discovery arrived as one of the great surprises of the entire mission. Io's surface was covered in sulfurous plains of yellow and orange, marked by towering plumes rising hundreds of kilometers above the ground. It was a world alive with fire, orbiting a gas giant in the cold outer reaches of the solar system, a reminder that warmth and activity can arise in the most unexpected places. Voyager scientist Linda Morabito discovered Io's volcanoes not in a scientific image, but in a routine navigation photograph. She was examining the image to measure star positions when she noticed an unusual umbrella-shaped brightness rising from the edge of the moon. At first, she thought it might be another moon, or an artifact in the data. Slowly, it became clear she was looking at something no one had ever seen before, a volcanic plume erupting from another world. It was a discovery made in the quiet work of an ordinary morning. The volcano named Pila on Io was erupting during both Voyager flybys, separated by several months. When Voyager 2 arrived and turned its instruments toward the moon, Pila was still pouring material into space, its enormous plume painting a dark reddish ring across the surrounding terrain. The consistency of that eruption across two separate visits suggested a volcano of extraordinary power and persistence. Somewhere out beyond the asteroid belt, on a small sulfurous moon, a fire had been burning all along, patient, ancient, and utterly indifferent to the tiny machines that had come to witness it. Europa's surface was seen to be a smooth, cracked ice shell, hinting quietly at a vast ocean hidden beneath. The images that came back showed a world unlike any other in the solar system, pale and luminous, laced with long, rust-colored fractures spreading across its face like lines drawn in frost. There were almost no craters, suggesting the surface was young, renewed from below by some slow, warm process. Scientists looked at those delicate cracks and began to wonder, softly and with great care, whether liquid water might lie just beneath the ice. Ganymede was confirmed during the flybys as the largest moon in the entire solar system. Larger even than the planet Mercury, it drifts in a slow, steady orbit around Jupiter, carrying its ancient grooved terrain through the dark with quiet dignity. Voyager's cameras revealed a surface layered with both old cratered regions and younger ridged plains, as though the moon had rewritten parts of its own history over billions of years. There is something deeply restful about a world that large, moving so unhurriedly through so much space. Callisto's surface was found to be one of the most heavily cratered objects ever captured by a spacecraft camera. Every part of it was marked, layered, and worn, a record of billions of years of impacts preserved in near-perfect stillness. Unlike its livelier siblings, Callisto appeared geologically frozen, unchanged for an immense span of time. Looking at its surface was like reading the oldest page in the solar system's history, each crater a quiet notation left by something that passed through long, long ago. Let your body settle a little more deeply now, wherever you are resting. There is nothing you need to hold on to. Let your shoulders release. Let your jaw soften. Let your hands lie open and easy. Each breath moves through you slowly, like a tide that has all the time in the world. The day has already done its work. All that remains now is this, the quiet, the dark, and the gradual, unhurried drift towards sleep. Voyager measured Jupiter's magnetosphere, extending millions of kilometers outward into space, making it by far the largest structure in the solar system. This invisible magnetic bubble, inflated by Jupiter's enormous spinning core, reaches so far that if our eyes could see it, it would appear larger in our night sky than the full moon. Within it, charged particles are swept along vast invisible currents, flowing in great arcs through the dark. It is a structure of extraordinary scale, and yet it exists in complete unhearable silence. The gravity of Jupiter gave both spacecraft a powerful, invisible push, accelerating them onward toward Saturn, without burning a single drop of fuel. This elegant maneuver, borrowing momentum from a planet, had been understood mathematically for years. But Voyager proved it worked in practice. Each probe swung close to Jupiter, felt the pull of that immense gravity, and emerged from the encounter traveling faster and aimed precisely at its next destination. The solar system itself had become the engine. Voyager 1 reached Saturn on the 12th of November, 1980, after a journey of more than 3 years across the outer solar system. The spacecraft had traveled over 1.5 billion kilometers from Earth, crossing an emptiness so vast it is difficult to hold in the mind. As it drew close, Saturn resolved from a distant point of light into something breathtaking, a banded amber world encircled by its extraordinary rings, hanging in the dark like something from a quiet dream. The team on Earth waited hours for each signal to arrive. Voyager 2 arrived at Saturn on the 25th of August, 1981, nearly 9 months after its twin. It traced a slightly different path through the Saturnian system, allowing scientists to gather a second, complementary set of measurements. The two encounters together built a far richer picture of Saturn than either probe could have provided alone. There was something quietly beautiful about that. Two small machines launched days apart from the same Florida launch pad, each finding its own way to the same ringed world across the immensity of the outer solar system. Saturn's rings, long thought to be a few broad, smooth bands, were revealed by Voyager to consist of thousands upon thousands of individual ringlets, each one distinct. The images showed a structure of extraordinary intricacy, concentric circles nested within circles, like the surface of a still pond, crossed by countless ripples all at once. Some ringlets were sharply defined, others softly blurred at their edges. What had appeared from Earth as simple geometry turned out to be one of the most complex and delicate structures in the known solar system. Voyager discovered mysterious spoke-like features drifting across Saturn's broad middle ring, dark radial streaks that rotated with the ring system like shadows on a clock face. They appeared and faded over hours, defying the usual physics of orbiting particles. Scientists eventually came to understand them as clouds of fine, electrically charged dust, lifted above the ring plane by magnetic forces and floating there briefly before settling back. The thought of dust floating silently above those vast rings, lifted by invisible fields, carries its own kind of hushed wonder. Voyager discovered a small, elongated moon called Prometheus, quietly tending the narrow F-ring of Saturn like a patient shepherd. This little moon, only about 100 kilometers across, pulls and pushes at the ring's delicate strands with its gravity as it passes close by. The result is a series of gentle ripples and braids woven into the ring material, channels and kinks that shift and reform over time. It is a slow, unhurried dance between a moon and a ribbon of ice, playing out in the cold dark far from any sun. Nestled within a clear gap in Saturn's outermost broad ring, a tiny moon called Pan was later confirmed from careful study of Voyager's images. Pan is a diminutive world, rounded at its equator by a thick ridge of ring material. It has swept up over countless orbits. Its presence explained why that gap in the ring remained so cleanly empty. Pan had been clearing it all along, like a slow broom moving through fine, drifting snow. The discovery was made not in real time, but years later, by patient eyes reviewing old photographs. When Voyager turned its instruments toward Titan, Saturn's largest moon, it found something remarkable: a thick, substantial atmosphere, richer and denser than anyone had expected. The atmosphere is composed mostly of nitrogen, the same gas that makes up the majority of the air we breathe here on Earth. Trace amounts of methane and other organic compounds drift through it as well, giving Titan a chemistry that scientists have described as hauntingly Earth-like in some ways, though utterly alien in others. It is a world wrapped in its own kind of sky. No camera could pierce Titan's atmosphere to see what lay beneath. A thick blanket of orange photochemical haze, built up from sunlight, breaking apart methane and nitrogen molecules, wrapped the moon in an impenetrable veil. Voyager's images showed only that haze, layer upon layer of it, warm amber fading into deeper rust at the edges, like the last light of a long autumn evening frozen in place. The surface remained a mystery, hidden and patient, waiting decades more to be seen. There is something quietly restful about a world that keeps its secrets gently. Let your body settle a little more deeply now, into wherever you are resting. There is nothing you need to hold on to, nothing you need to remember or work out. Let your shoulders release, let your jaw soften, let your hands rest open and still. Each breath comes and goes on its own, slow and even, unhurried. You are here, you are safe, and the night is wide and quiet all around you. Simply let yourself drift a little further into stillness now. Voyager's instruments measured the pressure of Titan's atmosphere and found it to be about 1.5 times the pressure of Earth's atmosphere at sea level. That is a substantial sky, thicker and heavier than our own, pressing down on whatever surface lies hidden below. Standing on Titan, if one could, the air would feel close and dense, though the temperature would be far too cold for any human comfort, hovering around -179 degrees Celsius. It is a world of cold pressure and amber dark, with its own quiet weight. To study Titan as closely as possible, mission planners chose to send Voyager 1 on a steep diving path toward the Moon, a choice that came with a cost. That trajectory bent the spacecraft's course so sharply that it could no longer continue onward to Uranus or Neptune. The planetary tour for Voyager 1 would end at Saturn. It was a deliberate and considered trade, sacrifice the onward journey in exchange for the closest possible look at this shrouded, atmospheric world. The spacecraft gave up its path forward to give science something irreplaceable. The close passage around Titan did more than end Voyager 1's planetary tour. It permanently tilted the spacecraft's path out of the flat plane in which the planets orbit. The ecliptic plane is like a vast invisible table on which the solar system is arranged, and Voyager 1 was now climbing away from it, angled upward into the space above. It would never return to that plane. From that moment on, Voyager 1 was bound for a region of space no planet occupies, a slow, solitary ascent into the quiet above the solar system. While Voyager 1 gave up its onward path for Titan, Voyager 2 was carefully guided along a different course, one that preserved its ability to continue outward. The trajectory threading past Saturn was chosen with great precision, allowing the spacecraft to use Saturn's gravity to bend its path toward Uranus, still years away across the outer solar system. Voyager 2 would carry on, the sole emissary to the two farthest planets humanity had ever planned to visit. It was a quiet act of foresight, written into the mission long before either probe had left the ground. Among all the moons Voyager imaged at Saturn, one stood out for a feature so striking it became instantly memorable. Mimas, a small, icy moon, was found to bear an enormous impact crater called Herschel, spanning nearly one-third of the moon's entire diameter. The crater is so wide and deep that the moon itself looks almost designed, a smooth sphere marked by one vast circular scar with a central peak rising from its floor like a still point of stone. The thought that a single ancient collision left its mark so completely on an entire world carries its own kind of hushed immensity. Enceladus, another of Saturn's moons, was found to have a surface so bright and so unmarked that it seemed almost impossibly new. Most moons in the outer solar system are ancient, their faces worn by countless impacts over billions of years. But Enceladus glowed with a freshness that told a different story, one of recent change, of ice renewed, of something active stirring beneath that pristine white shell. Scientists believe the surface had been resurfaced not so long ago in geological terms, smoothed and refreshed by processes still quietly at work. After its encounter with Saturn, Voyager 2 did not arrive quickly at its next destination. More than 4 years passed as the spacecraft moved steadily outward through the outer solar system, traveling through a vast and unhurried darkness between worlds. There were no planets to visit, no moons to image, only the slow, patient crossing of an enormous distance. The spacecraft drifted onward, instruments still running, engineers still listening, the sun behind it growing dimmer year by year. It was a long, quiet passage through deep space. On the 24th of January, 1986, Voyager 2 reached Uranus, and it remains, to this day, the only spacecraft ever to have done so. No mission before or since has made that journey. The encounter was singular, unrepeated, a single careful look at a world that has otherwise kept its secrets entirely to itself. Everything humanity knows from close observation of Uranus came from those few hours, from that one crossing, from a spacecraft that had already traveled for nearly a decade to reach it. What Voyager found at Uranus was deeply unusual. The planet does not spin upright like most worlds. It rolls through space tilted almost entirely onto its side, with an axial tilt of about 98 degrees. This means its poles point roughly toward the Sun at different points in its orbit, giving it seasons of extraordinary length and strangeness. In a sense, Uranus orbits the Sun like a rolling sphere rather than a spinning top. Scientists still wonder what ancient collision tipped it so completely so long ago in the early life of the solar system. As Voyager 2 swept through the Uranian system, its cameras revealed worlds that had never been seen before. 10 new moons were discovered during that single flyby, small, dark, irregular bodies orbiting close to the planet, hidden until the spacecraft drew near enough to find them. Each one was a quiet discovery, a new piece of a system that had been almost entirely unknown. The solar system grew a little larger in those hours, its population of worlds expanded by 10 in the span of a single close encounter with a planet 4 billion kilometers from home. Let your body settle a little deeper now. If there is any remaining tension in your shoulders, your hands, your jaw, simply allow it to soften and release. You do not need to hold on to anything tonight. The day is finished, and all its details are already dissolving. There is nothing to solve, nothing to remember, nothing to decide. Just this quiet moment and the slow, easy rhythm of your own breathing. Let each breath carry you a little further from wakefulness, a little closer to the restful dark. You are safe and still, and it is time to sleep. Uranus held another surprise beneath its calm exterior. Its magnetic field was found to be tilted at about 60 degrees away from the planet's rotational axis, a significant and puzzling offset. On Earth, the magnetic poles wander somewhat, but remain roughly aligned with the spin axis. On Uranus, the magnetic field seems almost unmoored, angled sharply away from where one might expect it to emerge. Scientists still work to understand what deep interior structure could produce such a tilted, asymmetric field around a world already rolling on its side. Among all the moons Voyager examined at Uranus, Miranda was perhaps the most astonishing. Its surface bore terrain unlike anything scientists had encountered, a fractured, jumbled landscape of cliffs and ridges and canyons that seemed to belong to several different worlds stitched together. Ancient smooth plains lay beside deeply grooved regions and jagged escarpments, as though the moon had been shattered and reassembled, or shaped by geological forces of extraordinary complexity. It was a small world with a bewildering face, and every image returned from it posed new questions. On Miranda, one feature stands above all others, quite literally. A cliff face known as Verona Rupes rises to a height of roughly 20 kilometers, making it the tallest known cliff in the entire solar system. To stand at its base and look upward would be to see a wall of ice and rock ascending nearly 5 times higher than Mount Everest. The thought of that silent, towering escarpment on a small frozen moon, in the dim light of a distant sun, carries a kind of immense wordless grandeur, a reminder that the solar system holds wonders in even its most remote and overlooked corners. Uranus was also confirmed to possess a system of rings, though nothing like the broad, luminous bands of Saturn. These rings are dark and narrow, made of materials so dim they had only been glimpsed from Earth in 1977, when astronomers noticed starlight briefly dimming as Uranus passed in front of a distant star. Voyager's close passage confirmed what those faint dimmings had suggested, a family of thin, shadowy rings encircling the tilted planet, each one a delicate thread of darkness orbiting in quiet formation around a world already full of surprises. Voyager 2 discovered 2 additional rings at Uranus, bringing the total number of known rings to 11. These 2 newcomers were fainter and more tenuous than the others, barely distinguishable against the darkness of space. They had been invisible from Earth, their existence unsuspected until Voyager passed close enough to reveal them. Each one a thin, unhurried loop of shadowed material, circling the tilted planet in its own quiet orbit, adding 2 more delicate threads to an already intricate family. Unlike the richly banded atmospheres of Jupiter and Saturn, Uranus appeared almost entirely featureless when Voyager's cameras turned toward it. No towering storm systems, no bold latitudinal stripes, no swirling eddies of contrasting color, just a smooth, even sphere of pale blue-green, serene, and almost unmarked. Scientists believe a thick haze layer high in the atmosphere conceals whatever weather patterns might exist below. Uranus wore its calm like a veil, offering little to the eye but a still, luminous quietness. For all the wonders Uranus had to offer, Voyager 2's closest approach lasted only about 6 hours. 6 hours to gather what it could from a world 4 times wider than Earth, orbiting nearly 3 billion kilometers from the Sun. The spacecraft swept through its closest point and continued onward, cameras and instruments working steadily through that brief window. Then Uranus began to recede, slowly at first, then more swiftly, shrinking back into the darkness from which it had emerged, returning to its long, unhurried solitude. After leaving Uranus behind, Voyager 2 settled into a long, unhurried crossing toward Neptune, a journey that would take 3.5 years. 3.5 years of near silence, of cold and darkness, of the spacecraft gliding steadily outward through a region of space where the sun had dimmed to little more than a bright star. There was no destination to rush toward, no landmark to pass, only the slow accumulation of distance and the patient turning of the years as the probe drew ever closer to the outermost giant. As Neptune drew nearer, the engineers at the Jet Propulsion Laboratory faced a careful challenge. Voyager 2's systems had aged over more than a decade in space. Circuits that had operated flawlessly near Jupiter now needed coaxing, and the spacecraft's ability to point its cameras precisely had drifted over time. Engineers devised new software, adjusted timing sequences, and essentially retrained the aging probe to perform at its best once more. It was a quiet act of devotion, tending to a traveler far from home, preparing it for one final, extraordinary encounter. On the 25th of August, 1989, Voyager 2 made its closest approach to Neptune, the last planet on its grand tour. 12 years after leaving Earth, the spacecraft arrived at a world nearly 4.5 billion kilometers from the Sun. It was the same date, by a quiet coincidence, that Voyager 2 had reached Saturn 8 years before. The probe swept past Neptune at its closest point, instruments alive with data, completing a journey that had carried it across the entire breadth of the outer solar system. There is nothing you need to hold on to right now. Let your thoughts settle the way dust settles in a still room, slowly, without effort, finding their own rest. Feel the weight of your body, heavy and unhurried, sinking a little deeper. Your breath moves in and out on its own, easy and slow. You are warm and still, and there is nowhere to be but here. Let the quiet carry you. Let yourself drift gently toward sleep. When Voyager's instruments turned toward Neptune, they found a world far more alive than Uranus had appeared. Neptune's atmosphere churned with activity, and dominating its face was a vast oval storm system that scientists named the Great Dark Spot. It was roughly the size of Earth, a deep indigo hollow in the planet's cobalt-blue clouds, rotating slowly counterclockwise. Unlike the featureless calm of Uranus, Neptune wore its weather openly, a dynamic, restless world dressed in shades of deep blue, alive with motion even at the edge of the solar system. Neptune's atmosphere concealed something extraordinary beneath its blue beauty, winds of staggering speed. Voyager's instruments measured gusts exceeding 2,000 kilometers per hour, making Neptune home to the fastest winds recorded anywhere in the solar system. On a world receiving barely a fraction of the sunlight that warms Earth, such ferocity seems almost impossible. Scientists believe internal heat rising from Neptune's deep interior drives these immense atmospheric currents. Yet from a distance, the planet simply glows, serene and blue, betraying nothing of the fury moving silently within. During its brief passage through the Neptunian system, Voyager discovered 6 previously unknown moons orbiting the planet. Small, dark, and irregular in shape, these worlds had been invisible to Earth, base telescopes hidden by Neptune's brightness and the limits of the instruments of the time. Each one was a quiet revelation, a new member of a distant family, circling their blue giant in the cold and the dark. It is a gentle thought that even at the far edge of the solar system, there were still small worlds waiting to be found. Neptune's moon Triton was found to orbit the planet in a retrograde direction, moving opposite to Neptune's own spin. Almost every large moon in the solar system travels in the same direction as its planet's rotation, so Triton's backward path immediately told scientists something unusual had shaped its history. Voyager's instruments traced that orbit with quiet precision, a graceful, looping path, steady and unhurried, circling a blue world in the deep cold of the outer solar system. Triton's backward orbit suggests it was not born alongside Neptune, but was captured long ago from the Kuiper Belt, the broad ring of icy bodies lying beyond Neptune's path. Scientists believe that billions of years ago, Triton drifted too close to Neptune and was drawn in by the planet's gravity, eventually settling into its present orbit. That ancient capture reshaped Triton entirely. Tidal forces slowly circularized its path over immense spans of time, leaving behind the orderly, retrograde world Voyager found waiting. Among Voyager's most astonishing discoveries at Triton was the detection of active geysers erupting from the Moon's frozen surface. These were not water geysers but plumes of nitrogen gas, heated just enough by the faint warmth of the distant sun to break through the surface ice and rise several kilometers into Triton's thin atmosphere. They drifted downwind in dark streaks across the pale terrain, delicate and unhurried. It is a quietly remarkable thing that even on one of the coldest, most remote worlds ever visited, something still stirs. Voyager measured Triton's surface temperature at -235 degrees Celsius, placing it among the coldest known objects in the entire solar system. At that temperature, nitrogen itself freezes solid, coating the surface in a thin, glittering layer of ice. The cold is so profound, it is almost beyond imagination, and yet Triton holds it quietly, a still and frosted world, orbiting its blue giant in the dark. There is something almost meditative about such extreme stillness, a world reduced to its most essential, most elemental form. Voyager's cameras revealed that Triton's surface carries a soft, distinctive pinkish hue, a blush of color across an otherwise frozen world. Scientists trace this tint to a mixture of nitrogen frost and organic compounds called tholins, formed when sunlight and cosmic radiation slowly transform simple molecules over millions of years. That gentle rose color, drifting across the pale terrain, gives Triton an unexpected warmth in photographs, a reminder that even in the coldest, most distant corners of the solar system, chemistry quietly works, patient and unhurried, painting worlds in colors no one expected to find. With the Neptune flyby complete, Voyager 2 had accomplished something no spacecraft had done before or has done since: a continuous journey through the four outer planets, gathering the solar system's distant worlds into one long, unbroken story. The planetary Grand Tour, first imagined decades earlier as a rare alignment of opportunity, had been fully realized. Every planet from Jupiter to Neptune had been visited, observed, and understood more deeply. The mission had traveled farther and revealed more than almost anyone had dared to hope when two spacecraft lifted quietly into the sky in the summer of 1977. After leaving Neptune behind, Voyager 2 was directed southward, angling gently below the flat plane in which the planets orbit the Sun. This trajectory was a deliberate choice, sending the spacecraft on a path that would carry it beneath the solar system's disk and out into interstellar space from below. The two Voyagers were now heading in different directions, one arcing upward above the ecliptic, one curving away below, like two quiet travelers parting ways at the edge of a vast and open country, each carrying the same message into different corners of the dark. Let your body settle a little more deeply now. There is nothing to follow, nothing to hold. Feel the places where you are resting against something solid. The bed beneath you, the pillow cradling your head, and simply allow that support to take your full weight. Your breath moves on its own, slow and even, like a tide that needs no direction. Thoughts may drift through, and that is fine. Let them pass like distant lights, unhurried, fading. You are safe and still, and the night is very quiet. Let yourself go a little further into that stillness. In 1990, the astronomer and writer Carl Sagan proposed something unusual: that Voyager 1's cameras, still technically functional though long since turned away from the planets, should be pointed back toward the inner solar system one final time. Sagan believed that looking back from that immense distance might offer something more than science, a perspective, a feeling, a quiet reckoning with our place in the universe. It was a gentle and deeply human idea that a machine traveling farther from home than anything ever built should pause just once and look back. On February 14, 1990, Voyager 1 turned its cameras inward and captured a mosaic of 60 frames that together formed the first portrait of our solar system seen from the outside. From 6 billion kilometers away, the planets appeared as tiny sparks of light, barely distinguishable from the surrounding dark. Earth itself was a fraction of a single pixel, a pale blue point adrift in a sunbeam. The image was called the family portrait, and it gathered the whole of our known planetary neighborhood into one still unhurried frame, as if the solar system itself had paused to sit quietly together. Carl Sagan's reflection on the pale blue dot became one of the most quoted passages in all of science writing. He wrote of that tiny point of light as a mote of dust suspended in a sunbeam, and reminded us that every human being who ever lived had spent their life upon it. His words arrived not as a lecture, but as a kind of tender acknowledgement that we are small, yes, but also that our smallness is something to be held gently, not with despair. The passage has been read aloud at memorials, at graduations, at bedsides, wherever people gather to feel the quiet weight of being alive. After the family portrait was complete, Voyager 1's cameras were permanently powered down. There was no ceremony, no final image, simply a command sent across 6 billion kilometers, and then the lenses went dark forever. It was a practical decision, made to conserve the dwindling electrical power the spacecraft would need for its instruments and transmitters in the long years ahead. The cameras had done extraordinary work across more than a decade. Now they rested quietly as the spacecraft continued its outward journey through the dark. Both spacecraft continued moving steadily outward, deep into the heliosphere, the vast bubble that the sun creates around itself and everything within it. This region extends far beyond the outermost planets, stretching into space for enormous distances in every direction. Within it, the sun's influence is felt as a kind of invisible presence, a constant breath of charged particles filling the space between worlds. The two Voyagers were still inside that breath, still technically within the sun's domain, traveling through a region most of us never think about and almost nothing had ever visited. The heliosphere itself is born from the solar wind, a continuous outpouring of charged particles, mostly electrons and protons, streaming away from the sun in all directions at enormous speed. This wind never stops. Day and night, across every season, the sun exhales this invisible river of particles into space, and it is that steady exhalation that inflates the heliosphere and holds it open against the surrounding interstellar medium. It is one of the quieter wonders of our solar system, an enormous invisible structure created simply by the sun breathing outward, as it has done for billions of years. As the years passed and the Voyagers moved ever farther from the sun, scientists began watching their data carefully for signs of a particular boundary, one that had been theorized for decades but never directly observed. This boundary marked the place where the solar wind, having traveled so far from its source, would finally begin to lose its strength. Researchers studied the readings from the spacecraft's plasma and particle instruments with patient attention, looking for the subtle shift in numbers that would signal something new. The waiting itself had a kind of stillness to it, a long, unhurried vigil at the edge of the known. The termination shock is the name given to the boundary, where the solar wind abruptly slows down. For billions of kilometers, the solar wind races outward at tremendous speed, but eventually it meets the pressure of the interstellar medium, pushing inward from all sides. At that meeting point, the wind is forced to slow suddenly, like a river encountering a dam. The particles pile up, compress, and heat. It is not a wall you could see or touch. It is a change in the nature of the space itself, a quiet but definitive threshold where the sun's reach begins to falter. Voyager 1 crossed the termination shock in the year 2004 at a distance of roughly 94 astronomical units from the Sun, nearly 94 times the distance between Earth and the Sun. The crossing was confirmed by a sudden change in the readings from the spacecraft's instruments. The solar wind slowed, particles compressed and heated, and the magnetic field shifted. It was a moment scientists had anticipated for years, and when it came, it arrived not as a dramatic event, but as a quiet change in numbers on a screen, a threshold crossed in the dark, unwitnessed by any eye. Voyager 2 crossed the same boundary 3 years later, in 2007, at a somewhat closer distance of about 84 astronomical units from the Sun. The fact that the two crossings happened at different distances told scientists something important: that the heliosphere is not a perfect sphere. The termination shock bulges and shifts depending on the direction, shaped by the uneven pressure of the interstellar medium surrounding it. Having two spacecraft cross at different points gave researchers their first real measurements of this asymmetry, two data points in an otherwise invisible and unreachable structure. Let your thoughts slow down now, just a little more. There is nowhere to arrive tonight, nothing to figure out. Feel the weight of your body, heavy and at ease, sinking gently into whatever is beneath you. Your breath is slow and natural, in and out, like something that has always known what to do. The room around you is still. The night is long and unhurried. You have done enough today. Let your eyes stay closed. Let your jaw soften. Let your shoulders release. You are drifting, very gently, toward sleep. Beyond the termination shock lies the heliosheath, a wide, turbulent outer layer of the heliosphere, where the slowed solar wind churns and mingles before reaching the true edge of the Sun's domain. It is not a calm region. Particles there are compressed and heated, the magnetic field tangled and irregular, the flow of material slow and uneven compared to the orderly rush of the solar wind closer to home. Scientists had imagined it might be relatively simple, but the Voyager data revealed something far more textured, a thick, complex shell of activity wrapping the entire solar system in a slow, restless embrace. The heliosheath turned out to be far thicker and more layered than scientists had imagined it would be. Theoretical models had sketched a relatively modest shell, a transitional zone of manageable depth, but the Voyager data told a different story. The region stretched on and on, tens of astronomical units wide, filled with slow-moving, compressed solar material, and a magnetic field that twisted and folded in unexpected ways. It was as though the Sun's outermost breath lingered far longer than anyone had thought, reluctant to dissolve into the interstellar dark. Among the most surprising discoveries within the heliosheath were enormous magnetic bubbles, vast, self-contained structures of solar material tangled into loops and coils. Voyager instruments detected these bubbles as regions where the magnetic field folded back on itself, creating pockets hundreds of millions of kilometers across. Scientists had not anticipated finding such structures so far from the Sun. They suggested that the boundary region of our solar system is far more dynamic and magnetically rich than the smooth fading edge that earlier models had envisioned. For years, scientists debated among themselves exactly when Voyager 1 would finally cross into true interstellar space. The spacecraft was clearly approaching the boundary, but the precise moment proved elusive. Different instruments gave conflicting signals. The magnetic field behaved unexpectedly. Some researchers announced the crossing had already happened, only for further data to suggest it had not. The discussion was patient and careful, a quiet scientific conversation carried on across years, as the spacecraft drifted steadily outward, indifferent to the debate, moving through the dark at its own unhurried pace. The heliopause is the outermost boundary of the Sun's influence, the place where the outward pressure of solar wind finally meets the inward pressure of the interstellar medium, and the two forces reach equilibrium. Neither pushes further than the other. It is not a wall or a hard surface, but a soft and shifting membrane, a place of balance suspended in the dark. On one side lies everything shaped by our sun, every planet, every moon, every comet and drifting particle born from that ancient star. On the other side lies the wider galaxy, ancient and immeasurably vast. On the 25th of August, 2012, Voyager 1 crossed the heliopause and entered interstellar space. It had traveled for nearly 35 years to reach that threshold. The crossing itself was not announced with fanfare in the moment. The data needed careful analysis before scientists could be certain. But eventually, the numbers confirmed it. A spacecraft built by human hands, launched from a small blue planet, had passed beyond the boundary of the solar system and entered the vast ancient medium between the stars. It was, by any measure, one of the most extraordinary things our species has ever done. The crossing date was not confirmed immediately. It was only in 2013, when scientists analyzed measurements of the density of the plasma surrounding the spacecraft, that the evidence became clear and certain. Interstellar plasma is significantly denser than the plasma within the heliosphere, and Voyager's instruments recorded that shift unmistakably. The data, transmitted across billions of kilometers at the speed of light, arrived at Earth and told the story plainly. The boundary had been crossed on that August day in 2012, and the spacecraft had been drifting through interstellar space ever since, quietly and continuously. With that confirmation, Voyager 1 became the first human-made object in all of history to reach interstellar space. No spacecraft before it, no probe, no artifact of any kind had ever traveled so far. Everything ever launched from Earth had remained within the sun's domain, until this one. The thought settled slowly, like something heavy and warm. A small machine, assembled by human hands in a building in California, now drifts among the stars. It carries with it the accumulated effort of thousands of people, decades of careful work, and the quiet, enduring hope of a species that has always looked upward and wondered what lies beyond. At the moment Voyager 1 crossed the heliopause, it was approximately 121 astronomical units from the Sun, 121 times the distance between Earth and the Sun. That distance is almost impossible to hold in the mind. Light itself, traveling at its unvarying speed, takes more than 16 hours to cover that distance. The Sun, seen from where Voyager was at that moment, would appear as nothing more than the brightest star in the sky, brilliant still, but just a point of light among many, its warmth entirely unfelt, its gravity still present but faint, a thread stretched very nearly to its limit. On the 5th of November, 2018, Voyager 2 followed its companion across the heliopause, entering interstellar space at a distance of approximately 119 astronomical units from the Sun, slightly closer than Voyager 1's crossing point. The two different crossing distances, separated by years and by direction, gave scientists something invaluable, two independent measurements of the boundary taken from different angles. The heliosphere, it became clear, is not symmetrical. It is shaped by forces pressing in unevenly from the surrounding galaxy, a living, breathing structure rather than a perfect and unchanging sphere. Let your body grow heavy now, heavy and still. There is nothing to hold on to tonight, no thought that needs finishing, no question that needs an answer. Just the slow, even rhythm of your breath, moving in and out without effort, the way it always has. Feel the places where your body rests against the surface beneath you, and let those places soften a little more. The night is long and quiet around you. You are safe and warm and at rest. Let your thoughts drift the way light drifts, outward, gently, without direction. There is nothing to do now but sleep. Voyager 2's crossing of the heliopause gave scientists a second measurement point for the thickness of that distant boundary. Before Voyager 2 arrived, researchers had only a single data point, Voyager 1's crossing in 2012. Now, with two probes crossing at different places and different times, a more complete picture could be drawn. Two measurements, taken years apart and from different directions, allowed scientists to begin mapping the boundary not as a single line, but as a real, three-dimensional structure with measurable depth. What those two crossings revealed was something unexpected. The heliopause is surprisingly thin, spanning only a few astronomical units from one side to the other. For a boundary separating an entire stellar domain from the wider galaxy, that thinness is remarkable. Scientists had imagined it might be a broad, gradual transition zone, a slow fading from one environment into another. Instead, it appears more like a definite membrane, not sharp like the edge of a blade, but narrow and distinct, a clear and measurable line between the sun's reach and the open interstellar sea. When both probes entered interstellar space, the measurements they returned surprised many researchers. The interstellar medium, the material filling the space between stars, turned out to be denser and warmer than a number of theoretical models had anticipated. Scientists had imagined the space between stars as extraordinarily sparse and cold, a near-perfect emptiness. The Voyager data told a more textured story. The interstellar medium has its own character, its own subtle warmth, its own faint presence. The darkness between stars is not nothing. It is something quiet, something real. Voyager 1, drifting through that interstellar medium, detected something subtle and beautiful, a faint, steady hiss of plasma waves rippling through the material around it. Scientists recognized that hiss as the signature of the interstellar medium itself, confirming beyond any remaining doubt that the spacecraft was no longer inside the heliosphere. The plasma surrounding it was interstellar plasma, ancient and undisturbed, material that had never been touched by the sun's wind. That quiet hiss, traveling back across 22 light-hours of space, was the sound of a place no human instrument had ever listened to before. Both Voyager probes continue to send their findings home, and they do so through a remarkable network known as the Deep Space Network, a worldwide system of radio telescopes dedicated to communicating with spacecraft across the solar system and beyond. The network has been listening to the Voyagers for decades, patiently gathering the faint signals that arrive after traveling immense distances. Without it, everything the probes have discovered would remain silent and unknown. The Deep Space Network is, in its quiet way, the ear that the Voyagers whisper into. The Deep Space Network operates through three main facilities, placed carefully around the world so that as Earth rotates, at least one antenna is always facing the right direction. The facilities are located in Goldstone in the California desert, near Madrid in Spain, and outside Canberra in Australia. Together, they form a triangle around the globe, a relay of listening stations that never sleeps. Each site holds enormous dish antennas, some stretching 70 meters across, curved like great bowls turned toward the sky, waiting for signals thinner than whispers. The signals from Voyager 1 now take more than 22 hours to travel from the spacecraft to Earth, even moving at the speed of light. 22 hours, a full day's turning of the Earth, just for a message to arrive. When engineers send a command to Voyager 1, they must then wait more than 44 hours for a round-trip exchange. There is a profound patience built into every conversation with this spacecraft. Every question asked, every adjustment made, every response received. All of it unfolds across the span of nearly 2 days, stretched thin across the dark. When Voyager 1's signal finally arrives at Earth, it carries almost no power at all, roughly 20 billion times weaker than the energy stored in a small wristwatch battery. The antennas of the Deep Space Network must strain to hear it, drawing on the most sensitive receiving equipment ever built. That a coherent, information-bearing signal can be recovered from such extraordinary faintness is itself a kind of miracle of engineering. The universe swallows sound and light with ease, and yet, across all that distance, the little spacecraft's voice still reaches us. Voyager 2, traveling on its own trajectory below the plane of the solar system, is somewhat closer to Earth than its companion, and its signal takes over 18 hours to make the journey home. 18 hours is still an extraordinary span, the better part of a full day's light-speed travel, just to cross the distance between one small spacecraft and the world that built it. And yet that signal arrives, reliably carrying measurements and readings from a place no other instrument has ever been. Voyager 2 continues to report, steady and unhurried, from the edge of everything familiar. Both spacecraft transmit their data at an almost unimaginably slow rate, just 160 bits per second. That is far slower than the earliest dial-up internet connections most people remember, slower than nearly any form of digital communication used on Earth today. Yet from that trickle of information, scientists have assembled a detailed portrait of the interstellar environment. Every measurement matters. Every bit that arrives is carefully preserved. The slowness itself feels appropriate somehow, a deliberate, unhurried exchange between a distant traveler and the home it left behind so very long ago. Let yourself settle a little more deeply now. There is nothing to hold on to, nothing to figure out, nothing waiting for your attention. Let your shoulders drop. Let your hands rest open and still. With each slow breath, you are drifting a little further from the day, a little closer to sleep. The world outside is quiet. The night is soft and wide. You are safe and still and gently carried, just like a traveler moving through the dark, unhurried, and at peace. Over the decades, engineers have carefully and gradually switched off instruments aboard each Voyager to conserve the dwindling supply of power. It is a slow, considered process, not a failure, but a thoughtful tending. Each instrument that goes dark has already given everything it was built to give. The spacecraft grows quieter instrument by instrument, year by year, like a great ship slowly dimming its lights as it sails further into the night, carrying its memories onward. The power output of each radioisotope thermoelectric generator decreases by roughly 4 watts every year, a steady and inevitable consequence of plutonium decay. Plutonium-238 releases its energy slowly and faithfully, but even faithfulness has its limits. 4 watts per year is a small number, yet across nearly 5 decades it accumulates into a significant loss. The generators that once hummed with life have grown quieter, dimmer, their warmth fading the way embers fade long after a fire has done its work. By the year 2025, only a handful of instruments on each Voyager remain operational, where 10 science instruments once hummed together. Gathering data from every direction, now just a few quiet voices remain. Each one still sends its readings home across the vast dark, still doing its small and faithful work. There is something tender in that, a spacecraft reduced to its essentials, stripped of everything unnecessary, carrying on with what little warmth remains. Scientists expect that the last remaining instruments will lose power sometime in the late 2020s. No one can say exactly when. The timing depends on how the power fades and how carefully the team manages what remains. But the end is near now, measured not in decades, but in years. It will come gently, not with any drama, simply a last reading, a last transmission, and then a long, unhurried silence settling in across the distance. Even after every instrument has gone dark and the last signal has faded, each Voyager spacecraft will continue drifting through interstellar space, silent and steady. There is no friction out there to slow them, no force to pull them off course. They will simply keep moving, carrying their momentum forward through the dark for billions of years. The mission will end, but the journey will not. The spacecraft will travel on, unhearing and unseen, long after every human who built them has turned to dust. Each Voyager spacecraft carries a golden record, a gold-plated copper disc containing sounds and images of Earth, sealed inside an aluminum cover and mounted to the spacecraft's exterior. It was placed there not as a scientific instrument, but as a greeting, a message from humanity to whatever or whoever might one day find it drifting among the stars. It is one of the most quietly extraordinary things ever launched into space, a small, shining circle of human life, riding on the edge of forever. The Golden Records were conceived and assembled by a committee chaired by Carl Sagan, the astronomer and writer whose gentle love for humanity and the cosmos shaped so much of how the world thinks about our place in the universe. Sagan gathered scientists, artists, musicians, and thinkers to decide what Earth should say to the stars. The process was careful and full of wonder, choosing which sounds, which voices, which images might speak for all of us. It was, in its own way, an act of profound and hopeful love. The records carry greetings spoken in 55 human languages, ranging from ancient Akkadian to modern Mandarin, and one message in the language of humpback whales. Each greeting was recorded with care, a voice reaching out across time and distance to say simply, "We are here, we are alive, we wish you well." The whale song is perhaps the most quietly moving of all, a reminder that humanity was not the only voice Earth chose to send into the dark. The music on the Golden Record spans the full breadth of human culture, from the mathematical intricacy of Johann Sebastian Bach to the warm, rolling joy of Chuck Berry's Johnny B. Good to the ancient, ornamented beauty of Azerbaijani folk songs. These pieces were chosen because they speak in ways that words cannot, reaching across all barriers of language and time. Somewhere out in the interstellar dark, a small copper disc carries the sound of humanity at its most alive, and that thought, held gently, is enough to carry you toward sleep. 116 images are encoded in the grooves of the Golden Record, each one a small window into what it means to live on Earth. They show the human body in careful anatomical detail, mountain ranges and quiet shorelines, a family sitting down to a meal, a child learning to walk. These images were not chosen to impress, they were chosen to simply say, "This is us, this is where we live, this is what our days look like." Each one is a whisper across the dark. Let your body settle a little more deeply now. There is nothing you need to hold on to, nothing you need to figure out. Let your shoulders release. Let your hands rest open and still. Each breath you take is slower and quieter than the last. The thoughts of the day are drifting away now, like light dissolving at the edge of evening. You are safe, you are still, and there is nowhere else you need to be. Simply rest. Etched into the cover of each Golden Record is a diagram, a set of careful, precise instructions for any finder who might one day hold it in their hands. The diagram shows the spinning motion needed to play the disc, the frequency of the pulses that encode the images, and a map showing the location of Earth relative to a set of pulsars, those spinning stellar beacons whose rhythms are as unique as fingerprints. It is a return address written not in any language, but in the universal grammar of physics. Tucked alongside each Golden Record, secured carefully in its aluminum housing, is a stylus, a small, diamond-tipped needle, ready to play. The people who built the record thought of everything. If some distant intelligence were to find it, they would not need to search for a tool. Everything required is already there, waiting. It is a gesture of extraordinary thoughtfulness across unimaginable distance, a gift wrapped so carefully that even the means to open it is included. The Golden Record was built to endure, designed to survive intact for at least 1 billion years, drifting through the vacuum of interstellar space. Gold does not corrode, and in the near-perfect emptiness between stars, there is almost nothing to wear it away. The disc that carries Baff and whale song and the image of a sleeping child will still be whole long after the continents of Earth have rearranged themselves beyond recognition. It is, in its quiet way, the most durable thing humanity has ever made. Voyager 1 is traveling in the direction of the constellation Ophiuchus, the Serpent-Bearer, a broad, ancient pattern of stars that stretches across the southern sky. It will never reach those stars, of course. They are incomprehensibly far beyond the probe's path. But the constellation gives us a direction, a way of pointing into the darkness and saying, "There, that way, something of ours is drifting." Right now, as you rest, it is moving through the dark in that direction, steady and unhurried. Voyager 2 is moving in a different direction entirely, outward and downward below the plane of our solar system, heading roughly toward the constellation Telescopium, a small, unassuming grouping of stars in the southern sky. The two probes are now separated by an enormous distance, each carrying its golden record into a different corridor of the galaxy. They left together, and now they travel alone, two quiet messengers moving through the dark in their own chosen directions. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445, a dim, reddish dwarf star in the constellation Camelopardalis. It will not come close enough to be captured or even to be seen as more than another distant point of light. But for a moment, measured in the deep time of the cosmos, the spacecraft and that quiet star will be nearer to each other than either is to anything else. A brief nearness across the dark, and then onward. In that same span of 40,000 years, Voyager 2 will make its own quiet passage, drifting to within 1.7 light-years of a star named Ross 248, another small red dwarf, this one in the constellation Andromeda. The two probes, launched within weeks of each other from the same small world, will each have their own moment of stellar proximity, separated by the width of the sky. Two travelers, two paths, each finding their own brief neighbor in the immensity. Neither Voyager will ever fall into orbit around a star. The distances involved are simply too vast, and the probes are moving too swiftly and at too great an angle for any stellar gravity to claim them. They will pass by, as they have always passed by, unhurried, unbound, belonging to no sun. They are free travelers now, in the truest sense, moving through the galaxy on trajectories that will carry them onward, essentially forever. That thought, held gently, is a deeply restful one. Once the Voyagers fall silent, they will continue drifting through the Milky Way as permanent residents of the galaxy itself. With no engine to slow them and no gravity strong enough to claim them, they will simply keep moving, tracing long, sweeping arcs around the galactic center, completing one full orbit every 250 million years or so. Long after every instrument has gone quiet, long after every signal has faded, they will still be out there, turning slowly with the galaxy, endlessly and without effort. In roughly 300 years, both Voyager spacecraft will reach the inner edge of the Oort cloud, the outermost frontier of our solar system's family. 300 years is a long time by human measure, a span that carries us back to the age of candlelight and wooden ships. And yet in the life of the solar system, it is barely a breath. The probes are already moving toward that threshold, unhurried and steady, crossing the dark one quiet kilometer at a time. Let your body settle now, just a little more. Let your shoulders release, let your hands rest open and still. There is nothing to hold on to tonight, nothing to carry forward. Each breath you take moves through you slowly, like a tide that knows exactly where it is going. You do not need to think or plan or remember. You are here and you are safe, and the night is long and quiet around you. Let your thoughts grow lighter, like objects drifting free of gravity, floating gently upward and dissolving into the dark. The Oort cloud is a vast, spherical shell of icy bodies that surrounds the entire solar system in every direction. It is not a flat disk like the asteroid belt, but a globe, a hollow sphere of frozen material stretching outward from the sun in all directions at once. The objects within it are thought to number in the hundreds of billions, each one a small, dark traveler of ice and rock, drifting in near-perfect silence at the very edge of the sun's gravitational reach. We have never directly seen it, but we know it is there. It will take the Voyagers approximately 30,000 years to pass completely through the Oort cloud. 30,000 years ago, our ancestors painted animals on cave walls by firelight, and the last ice age was only just beginning to release its hold on the land. The probes will travel through all of that time again, and then through all of it once more, simply crossing this one vast, quiet region of our own solar system. The scale of it is almost too large to hold, and yet it rests in the mind like something soft. The interstellar medium through which the Voyagers now travel is not empty, even though it may seem so. It is threaded with extraordinarily sparse clouds of hydrogen and helium gas, with microscopic grains of dust, with faint magnetic fields that weave through the dark like invisible currents. The density is almost incomprehensibly low, just a few atoms per cubic centimeter, and yet it fills all of interstellar space with a kind of invisible texture. The Voyagers are not moving through nothing. They are moving through something ancient, diffuse, and everywhere. As the Voyagers moved beyond the heliopause, their cosmic ray detectors began registering a different kind of particle than those found inside the heliosphere. Cosmic rays from interstellar space arrive from all directions equally, with a different energy signature than the particles accelerated by our own sun. The Voyagers confirmed this distinction directly, providing the first in-place measurements of the interstellar cosmic ray environment. It was a quiet but meaningful discovery, proof that the radiation filling the galaxy has its own distinct character, its own ancient origin. The data the Voyagers have returned about the heliosphere has helped scientists build more accurate models of how that vast magnetic bubble protects life on Earth. The heliosphere deflects a significant portion of interstellar cosmic rays before they can reach our planet. Without it, the radiation environment near Earth would be noticeably more intense. Understanding its true shape and thickness, something only Voyager could measure directly, has deepened our appreciation of how sheltered our small world really is, cradled inside a magnetic envelope that spans billions of kilometers. The Voyager mission has now lasted over 47 years, far beyond the original 4-year design life that engineers planned for back in the 1970s. The spacecraft were built to survive the rigors of the planetary tour, and perhaps a little beyond, but no one truly expected them to still be transmitting nearly 5 decades later. They have outlasted the careers of the people who built them, outlasted entire generations of technology, and continued speaking quietly across the dark long after anyone thought they would still have something to say. Today, the Voyager mission is managed by a small, dedicated team of engineers, and some of them were not yet born when the probes launched in 1977. They learned the ancient systems from those who came before, inheriting a kind of stewardship, tending to 2 spacecraft older than themselves, listening for signals that take more than a day to arrive. There is something quietly moving about that. A mission passed from hand to hand, across generations, kept alive by care and patience, the way any good and lasting thing is kept alive. In 2022, engineers solved a quiet mystery that had been puzzling the Voyager team for some time, an unexplained glitch in Voyager 1's attitude control system data. The spacecraft had been returning corrupted readouts from the system that keeps it properly oriented in space, and no one was quite certain why. After careful analysis, the team traced the problem to a single faulty digital voltage regulator. The fix was delicate, the distance immense, but the signal went out and the answer came back steady and clear. Then, in 2023, something more serious unfolded. A memory chip inside Voyager 1 failed, and for several months, the spacecraft transmitted only garbled, unreadable data back to Earth. The signals arrived, they always arrived, but the words made no sense. The team could hear the spacecraft speaking, but could not understand what it was saying. It was a strange and tender kind of silence, like receiving a letter written in a language that had suddenly become scrambled. The team listened and waited and thought. In 2024, engineers found a way through. Rather than replacing the damaged memory chip, something impossible across more than 22 light-hours of distance, they rerouted the spacecraft's code so it simply worked around the broken section entirely. Instructions were redistributed across other memory locations, the way a river quietly finds a new path around an obstacle. The solution took months of careful planning, and when the repaired code finally took hold, Voyager 1's voice came back, coherent, steady, and unhurried as ever. Let yourself settle a little more deeply now. There is nothing left to hold on to tonight, no task waiting, no thought that needs your attention. Simply feel the weight of your body resting where it is, heavy and still. Let your breath move slowly, in and out without effort. Each exhale carries a little more of the day away. You are here, and you are safe, and the dark around you is as soft and wide as open space, full of nothing but stillness and rest. Let yourself drift. The repair of Voyager 1 in 2024 was not a simple matter of sending a quick message. Every command transmitted to the spacecraft must travel more than 22 hours at the speed of light before it arrives, and then the response takes another 22 hours to return. The entire round trip spans 45 hours. Engineers would send an instruction, then wait nearly 2 full days to learn whether it had worked. Each step of the repair unfolded in this vast, patient rhythm: action, silence, answer, stretched across the dark like a slow and careful conversation. Voyager 1 is now the most distant human-made object ever to leave the Earth. No other spacecraft, no rocket stage, no artifact of any kind has traveled farther from our world than this small, golden antennae craft drifting through interstellar space. It crossed a distance that no human mind can truly hold, billions upon billions of kilometers, and it is still moving outward, still receding, adding to its own record with every passing hour. The title it holds is not one anyone will take from it for a very long time. Together, Voyager 1 and Voyager 2 represent the longest-running active deep space mission in the history of human spaceflight. For more than 4 decades, they have continued operating, continuing to return data, continuing to extend our reach into the unknown. No other mission has remained in contact with spacecraft so far away for so long. They are a testament to what endures: careful engineering, devoted attention, and the slow accumulation of years spent listening across an almost incomprehensible distance. Something about their persistence feels like a quiet kind of faithfulness. The legacy of Voyager has already begun to shape the next generation of deep space exploration. Scientists and engineers are conceptually designing future interstellar probes inspired by what the Voyagers taught us, missions imagined for the 2030s and the decades that follow. These future spacecraft might travel faster, carry more capable instruments, and reach the heliopause in years rather than decades. The Voyagers open the door. Those who come after will walk through it with the benefit of everything these 2 quiet travelers learned along the way. Before the Voyagers flew, the outer solar system was largely a mystery, a collection of distant points of light observed only through telescopes. The Voyagers transformed those abstractions into worlds. They gave us volcanoes on a moon of Jupiter, braided rings around Saturn, a tilted and storm-swept ice giant, and a captured moon with nitrogen geysers erupting into the dark. They revealed a solar system far stranger, far more varied, and far more alive with activity than anyone had imagined. The universe, the Voyagers showed us, is always more surprising than our best guesses. And then there is the pale blue dot, that single tiny fragment of light photographed from more than 6 billion kilometers away. Our entire world reduced to a mote suspended in a sunbeam. It remains one of the most philosophically resonant images ever made. In it, every person who ever lived, every joy and every sorrow, every civilization and every ruin exists within a speck almost too small to see. The image does not diminish us. It reminds us with extraordinary gentleness of how precious and improbable this small, bright world truly is. Voyager's journey reminds us that the cosmos is vast, ancient, and largely unhurried beyond our tiny world. Out there between the stars, there is no sound, no weather, no rushing current of time as we feel it here. There is only the slow turning of the galaxy, the faint whisper of interstellar gas drifting in the dark, and two small silver travelers moving outward in silence. We sent them from this fragile, luminous world, from a place of birdsong and tides and sleeping children, and they carry something of all of it with them, forever. The universe is immeasurably old, immeasurably wide, and in its great stillness there is something that asks nothing of us except, perhaps, that we rest. So let that vastness hold you now. Let the distance be a comfort rather than a weight. Somewhere far beyond any horizon you will ever see, Voyager 1 and Voyager 2 drift on through the dark, unhurried, faithful, and at peace. And here, on this pale blue world they left behind, you too can be still. You are held by the same universe that holds them. You are part of the same ancient story. Let your breathing slow. Let your thoughts grow soft and distant, like signals traveling across the deep. You have done enough today. The cosmos will continue its quiet turning while you sleep. Good night.